So good morning, everyone. Thank you for joining our April IMEDS community call today. This is Christine Yu from the Reagan-Udall Foundation. Please note that this group has now been put on mute for the time being to cut back on the background noise, and we will be unmuting everyone at the end of the presentation for a question and answer period. A few in-house announcements before I turn the presentation over to Dr. Lambert. In the IMEDS lab, we have completed and qualified by the Mini-Sentinel QA process the Mini-Sentinel CDM claims and Medicaid data sets. We have the Medicaid CDM data set in the Redshift and SAS format now available, and the claims data set will be available soon. Also, the OMOP CDM version 5 for Medicare, Medicaid, and claims is now available in the Redshift format. In addition to this, we'd also just like to let everyone know that as one of the IMEDS Research Agenda projects we awarded last year, Dr. Todd Lee's group at the University of Illinois in Chicago has established a Center of Excellence with the goal to follow cross-disciplinary research that have an impact on the ability to monitor post-market drug safety and also to synthesize these findings for the larger community. We're happy to announce that they have just launched an initial website, and we will be sending an e-blast to this group in a few weeks with more information and a link to this website as well. Dr. Lee will be presenting on the June IMEDS community call, so for anyone who is interested to know more about this project, we strongly encourage you to join us for that call. So for today's presentation, we have Dr. Christophe Lambert, who is an associate professor from the University of New Mexico and also a member of the OHDSI collaboration, here to present to us a research he's been working on in the IMEDS lab. This work has recently been accepted for publication, so congratulations to the authors and everyone who's been involved in the project. You should be able to see the presentation on your screen. Please note that this presentation is being recorded, and we will be putting a copy of it on our website after this call. So with that, Dr. Lambert, thanks very much for taking the time to present to us today. Without further ado, I'll now turn the presentation over to you.
Well, thank you so much, Christine. Can you hear me well?
Yes.
Good. We had a helicopter fly by right next to the hospital here, so I'd really like to thank you for this opportunity to present our work. This work started back in 2014 when we applied for access to the IMEDS lab to do this large-scale observational research on electronic health records, administrative claims data. And our vision has been, how do we really derive high-quality evidence from this large-scale data to answer questions that may not be asked by clinical trials. And the IMEDS resource has been a really wonderful thing to work with, and I'm glad we can finally present our work. So in terms of disclosures, I have no financial interests related to the current work, although I do receive income from a bioinformatics software company that I founded about 15 or 16 years ago. My presentation is going to first talk about some of the issues that we're working on in deriving high-quality observational evidence from EHRs. And when I say EHRs, I'm using it loosely to encompass also administrative claims data, which is your billing records. And then I'm going to talk about this work that's recently accepted for publication, where we've looked at large-scale data and derived relationships between bipolar disorder treatments and outcomes or hypothyroidism, looked at 9 different drug therapies and compared their outcomes over time using survival analysis-based approaches. And then talk about how some of our current work that's ongoing on further extending methodology, and show a couple other examples of some data analysis on longitudinal data. So the challenge is really to extract reliable, we'd love causal, or at least predictive relationships between treatments and outcomes to inform better decisions. And the OHDSI Collaborative, a number of us co-authored a paper a couple years back where we laid out a vision for a large-scale evidence base, and Richard Boyce is really the leader on this effort, and the idea is that we want to be able to look at really all drugs crossed by all outcomes of interest, health outcomes of interest, and create a high-quality evidence base. And obviously, there's many questions that are never going to be answered with randomized controlled trials that give us, on the good side, they're a gold standard for causal inference. They're very good for answering a specific question, rigorous, and especially they eliminate sample and selection bias, controlling known and unknown variables through randomization, much more likely to find causality. The downside of randomized controlled trials is they're limited, homogeneous, generally healthier populations, usually a shorter time period. They're focused on one or a few questions, and so you can't cast your net broadly to derive a whole lot more evidence out of such studies. And often they have low power for, say, complex polypharmacy questions. And of course, there's many populations rarely studied. Most clinical trials are going to incorporate people who are mostly healthy other than the disease of interest. And so the vulnerable, the old, the young, often we don't have great evidence. And so in the absence of being able to do these types of expensive and time-limited studies, we of course have the world of large-scale electronic health records, administrative claims data. They have a lot of the benefits, or in terms of, their pros often counter the cons of randomized controlled trials in that they reflect real-world settings, can measure long-term patient outcomes. The study I'm going to show, we looked at 4 years. In fact, but the models went all the way out to 7 years. And we can include heterogeneous patient subgroups, and of course have large sample size to really tease out differences that you might not have power otherwise. The downsides, of course, and this is really where we work on methods, and there's downsides besides this in terms of noisy data and so forth, but the biggest one we really are worried about is how do we derive high-quality evidence when there's potential biases and confounders. There's also questions about the best ways to stage data, and one of the really neat things that came out of the OHDSI effort, especially back when it was called OMOP some years ago, was this large study showing that with many different data sets, different statistical methods, when you went to try to answer so-called known, quote, ground truth health outcomes of interest, especially adverse drug reactions, you could get very different answers depending on the data set, the parameters used. So honest statisticians could even use the same method with the same data, but a variation in parameters and get different directions of odds ratios. And so one of the real thrusts of the OHDSI effort is to say, let's have a suite of analytical approaches across a suite of data sets so that we can weigh that body of evidence and see what the distribution over many approaches is. And if it is weighted heavily one way, well, we have more confidence we may act on that evidence. So the OHDSI effort, recently we tallied up that over 600 million patients have been mapped to this OHDSI common data model, which is a database schema that I'll show briefly next. And one of the advantages of collaborative is there's a whole lot of tools that are being jointly developed and made available in a GitHub repository. And this includes being able to visualize the data, look at data quality issues, extract transform load processes of pulling it out of that longitudinal format and getting it ready for some sort of statistical analysis. And then there's methods for comparing treatments and outcomes, and of course this knowledge base that's being built to hold all of the repository of information. And so we're not meant to look at all this fine print, but really what is the OHDSI Common Data Model? It's really a database schema Also includes vocabularies that data is mapped to common vocabularies, for instance, drugs may be coded in different ways in different health systems, but they get mapped to RX norm and some higher level vocabularies. There's a notion of visits, procedures, conditions, those are your diagnoses, even cost information, observations. This is, by the way, Common Data Model version 4.5. This is what we had to work with over the last couple of years. The model's improved and gone up to version 5. But all the work I'll show today was based on this model. And so you really have this unit of a person and all the things that happen to that person over time stored in different tables, and one needs to design a study and extract relevant covariates and figure out how to analyze the data to address biases, confounders, and derive high-quality evidence. So the data source, again, we're grateful to the Reagan-Udall Foundation for providing access. This is market scan data from Truven Analytics. It's recently been updated to cover 2003 to 2014. Over 200 million unique patient identifiers. There may be overlap within them, but it's a huge set. It represents patients covered from anywhere from 1 day to 10 plus years, and on average it's several years. Unfortunately, there's limited lab data, but we do get procedures, diagnoses, some limited demographics in that there is age and sex, some geographic information, but limited. And of course, it's been mapped to this common data model, version 4.5. So the IMEDS project that we have been working on is really trying to build a system for deriving high-quality evidence. And so you've got different data sources, and as Christine was mentioning, additional ones are being added, but the ones that we've been working with for this study are actually this commercial claims and encounter database, which was 1.41 million at the time we did the study. There's also additional data from GE Health, Medicaid, and Medicare, and then across these different data sets, there's lab data for a small subset of maybe 1% of the patients in these populations. So the challenge is, here's a patient at a given time. There's some time period of history that the patient's been observed, demographics, medications, comorbidities, substance dependence, drug metabolism. So all that history of a patient, what makes them unique. And then we want to be able to assess a choice, medication A versus B. What would be your expected outcomes over time, both beneficial and detrimental? And that's what we set out to do. And a wonderful model system for us was bipolar disorder, something I've published some genetic studies in the past and have worked with collaborators who know a lot about the disease. And in particular, we were interested in hypothyroidism, in part because it's an important health problem, also because one of the oldest adverse drug reactions of hypothyroidism that's expected to be seen under lithium was what we were sort of starting at as a, quote, ground truth. And in the process of doing our analysis, we discovered some interesting things in comparing it with other drugs that prompted us to publish our findings. So hypothyroidism is a deficiency of where you have clinical thyroidism is a high TSH and a low T4. So the thyroid gland is not producing sufficient thyroid hormone despite getting the signal. Generally, historically, hypothyroidism has been associated with lithium deficiencies, and there's still parts of the world where goiter, which is caused by a deficiency in iodine, is very prevalent, and is more common in women than men, and has increased risk with age. But generally, in developed parts of the world with iodine in the salt in our diet, the disorders are often due to autoimmune disorders. And so here's the prevalence in the U.S., 1 to 2% for clinical, and then an important category is subclinical hypothyroidism, which has important ramifications for bipolar disorder, is as high as 21% in women and 16% in men. And what we'll see in this study is because of the testing bias, there may well be why it's so difficult to get a handle on these numbers is a lot of it is underdiagnosed. So in bipolar disorder, lithium, we had, of course, 1.2 million bipolar patients out of the commercial claims and encounter data. And for over 40 years, there's been publications on how lithium treatment is associated with increased risk of hypothyroidism. Now, it's treatable. You can get regular thyroid monitoring. It's indicated when you're on treatment, and you can manage it with thyroxine. The thing is, if it's not diagnosed or treated, even the subclinical hypothyroidism has real problems with treatment resistance and or rapid cycling. There's problems of both spending longer time in the acute manic phase and having higher depression scores during the maintenance phase. And so there's still some questions about, there is a higher incidence of hypothyroidism among bipolar patients, and there's questions of causality. Is it, which comes first, the hypothyroidism, which can be associated with depression, or the bipolar that's, or something that this is a tightly interconnected system that it's hard to say what causes what. So we're not going to be teasing out mechanisms with this, but we're mainly going to be comparing drugs, and so this is our study design. So we started with 141 million patients that were in the commercial claims encounters data, and then we required that there be at least 2 bipolar diagnoses, because just when you have just one, you can be concerned it might be a misdiagnosis or data entry error. And that restricted us to a more female population. And then we said there had to be a year of no bipolar disorder drugs and no hypothyroidism, and that cut the population to 200,000-ish. And then we said we're going to take adults only, 153,000. And then when we're looking at the data, we saw that there was plenty of patients who were not tested for their thyroid. And so to have more of an apples-to-apples comparison, we said let's ensure that there was at least one thyroid test during treatment. And that left us with 24,574 patients. That was our primary cohort, and we also looked at some sub-cohorts who are on at least 90 and 182 days of therapy. And so this publication has been accepted in bipolar disorders, and we hope it appears soon. And the gist of it, so there's a lot under the hood that, I could show you Python code. Now there's some new OHDSI tools to actually sort of predefine your cohorts with a user interface, and you can get SQL code to extract relevant covariates in patients. At the time, we didn't have access to those things, and we also even I think the current codes are not geared towards survival analysis. So a lot of times you'll have a fixed washout period like we do here, where we ensure that there's no exposure to the drugs and the conditions of interest don't occur. But then there's a variable time until event, and so we look at the time to either hypothyroidism or the ending of monotherapy, and we look at pretreatment characteristics during that 1 year, and so you could be missing things that happened to the patient, other pre-existing conditions that there was no treatment or care for in that year, but it's a reasonable period to characterize the patients in a uniform way, so they've all been seen for a year before treatment, and then we look at during that exposure, what treatment did they start on? We have to check that they're on a continuous exposure, or in our rule was a break of no more than 30 days. And then we look at what tests are done for thyroid testing and what types of visits occur. So the real challenge in all of this, I must say it was a challenge to get all the data staged and ready, but then when you get to the analysis is addressing the biases. So when we look at those pre-treatment characteristics, and we're looking at 9 different drugs, and they're listed across here. Lithium was our sort of gold standard and reference with which we compared to all these other ones. And then what we did here is compared for all of these pre-treatment covariates, the age of treatment, what medications that they had in the year before treatment, what mental diagnoses, what other relevant conditions, cardiovascular, pulmonary, etc., were seen. And we excluded hypothyroid conditions from all these categories. So one of the neat things about the common data model is there's these vocabulary hierarchies where you can say in a simple query, give me all diagnoses or all drugs who are children of apparent concept. So all musculoskeletal disorders or all endocrinopathy disorders. It might be, there might be 1,000 different codes for that, and you can basically roll it up into a single query. So the p-value in this column, the treatment bias p-value, is you do an association test looking at is there different proportions by drug, by age, by medication, etc. And we see huge significance for all of these. One interesting one was quetiapine was higher among those who had drug dependence, right? So we see 22% here, and it's much lower for all the other drugs. Turns out quetiapine is one of the few of these drugs that actually can be abused for a recreational high. And so if someone who's drug dependent is more likely to take or get a given drug, that's an important bias that one has to account for. So with treatment biases, it doesn't necessarily mean that they're significantly associated with the outcome. And later in the analysis, we looked at all of the associations with age, and found only a subset of these covariates were really relevant pre-treatment for bias correction. But we looked at them all. So one of the most important biases and challenging ones to address was in thyroid testing. And so the challenge is pre-treatment, you could look at thyroid testing, and we had that as a covariate, but post-treatment, it turns out there's a very different behavior that physicians are monitoring patients on lithium with a much more frequent testing of the thyroid than all of the other drugs. And we saw anywhere from 2.2 to 3 times higher testing levels of lithium from the most frequently to the least frequently tested of the other drugs when you fit these slopes. And so one of the tricks is you say, well, generally when you're doing any kind of a survival analysis, if you have a variable like testing, the number of tests is really highly correlated with how long you've been observed. And so if you were to put that in the model, it would totally mess up your regression. So we developed an approach that you could make a case for that pre-treatment you could specify, if you were designing a trial that had variation in testing, pre-treatment you could pre-specify different levels of testing. And so what we did is we ranked the testing frequency within bins of different lengths of exposure and created a normalized covariate for that and did a model both with and without that. So before we did a model with covariates, we first said, let's look at the cumulative incidence of hypothyroidism as a function of drug treatment. And so the y-axis here is the cumulative incidence over time, and this goes out to 4 years. the data started getting pretty sparse. We had it going out to about 7 years. We see, yes, lithium has this higher incidence. Now, is that a function of that it's truly the highest risk treatment, or, as we showed on the previous slide, how much of it is due to this treatment bias, and so or this testing bias? If you don't test for thyroid disorder, you're not going to find it. So, by the way, the cumulative incidence is is often used in a competing risks framework, and unlike so one of the things that we observed was really important here is there's really two risks that we're looking at plus censoring. So censoring is when the data ends before either any of your conditions of interest occur, and so that would correspond to the data ending in 2013, which is when we staged our data, and or before the data had been updated to 2014, and so there's a competing risk of hypothyroidism or the patient ending monotherapy. And by ending monotherapy, it's either adding an additional drug, because polypharmacy is common, or having a break in treatment of more than 30 days. So this graph on the right is looking at the other risk of basically ending monotherapy. And you see that there's some difference here, that lamotrigine actually, they stay on therapy a little longer, partly, we think, due to there's a titration period of getting people up to the right dosage with lamotrigine that may explain some of this. And so a regression approach that accounts for both the competing risk of getting hypothyroidism or ending monotherapy, whichever comes first, and having the right censoring is what we use, which is called competing risk regression. It's an approach by Fine and Gray, published in 1999. And so here on the left is after correcting for the covariates, and I'll show you the model in the next slide, but we see actually that lithium was statistically indistinguishable from quetiapine, and in fact, when we required that patients had at least 90 days of exposure, they were still statistically indistinguishable, but visually to the eye, the quetiapine risk was higher. Again, not statistically significant, but it was, as a whole, lithium was statistically significantly higher than the basket of all other drugs combined. So here's the model, and recall we had looked at subsets of both patients in addition to the 0 months, both greater than 3 months and greater than 6 months of monotherapy. And so this is the overall test, 3.8 times 10 to the minus third of lithium associated with hypothyroidism compared to the other treatments, and then we can look at individual treatments. And we also had our corrections for pretreatment thyroid testing, this post-treatment covariate that I described, and then non-hypothyroidism forms of thyroidism was an important covariate to adjust for. And so what did we see as the error bars of these estimates? So we found, interestingly, the risk is substantial on all treatments, and it's not to say all treatments are causing it. It may well be that this is the, somewhere around the baseline risk of having no treatment, for all we know. But and there's some technical reasons why one couldn't apples to apples compare to no treatment. And we see that the error bars overlap for all of these treatments. Quetiapine, the brand name Seroquel, is a particular note that it actually is the only drug, and just in 2013 the labeling was changed that there's enough incidences of hypothyroidism that they'd added thyroid testing to the labeling. And yet when you look at the difference among these, it's not huge. And so if there's a little drug effect that's, say, worse for lithium or perhaps quetiapine, we have to be concerned about all of this area under the curve here, where especially what we saw with the under-testing of patients on these other therapies, whether it's the therapy or just this natural disease progression. We know untreated hypothyroidism has important clinical implications. So we're also able to do error bars over time, and so this is 95% confidence estimates over 4 years. This is lithium in black compared to all the other treatments, and you can see that the there's a heavy error overlap. So historically, physicians have been almost exclusively focused on lithium as being of concern, and in fact, we need to think about really is bipolar disorder and hypothyroidism something that are intricately related, and we need to monitor patients for this throughout treatment. So some of the summaries of what we found in our study, that the range of the 4-year cumulative incidence was 8.8 for lithium, down to 6.3 for carbazepine, which is like a 1.39-fold difference, which is not huge. There was a significant difference. We don't want to minimize that. Lithium still does have risks associated with thyroid function, and there's some, good laboratory data showing those changes. But the significance of age, gender, thyroid testing are dwarf treatment by comparison. So when one considers risk factors for hypothyroidism in the treatment of bipolar, females have higher risk than males, and older people have a much higher risk. And so we need to think about that as we're monitoring patients. Lithium, as I said, wasn't statistically significantly different from quetiapine. And we saw in our data, despite, there is a known link between hypothyroidism and BD, only 40% of patients received a thyroid test in the year before or during monotherapy. They're tested much more frequently on lithium. And we looked at all the FDA labeling, and only lithium and quetiapine have labeling suggestions. So it's not necessarily to say that the drugs need label changes, but it's that we need to be aware that there's high thyroid risk with bipolar disorder, and we recommend that regardless of treatment, patients be regularly tested for clinical or subclinical thyroid abnormalities. And of course, it's a very treatable condition. So this ends the first part of my presentation on our forthcoming work. And what we've been working on in over these 2 years, in addition to this, are new methods that have been actually pushed by the analysis of this data. So I'm going to talk a bit about these methods now. So the limits we saw with competing risk regression is, they don't address nonlinearities. They force assignment of artificial covariates. So when you saw those curves that are covariate adjusted, if you call, I think about 60% of or 65% of the cohort was female. So you would have assigned a value for sex of 0.65, and there's no people in that study with 0.65 as a value for sex, either male or female. It assumes proportional hazards, i.e. that those lines don't cross. And so many of you perhaps heard with propensity scoring, there even are some survival-based approaches to propensity scoring. But one limitation of it is what propensity scoring does is say, let's predict what treatment a person is going to have based on their pretreatment covariates, and let's group them together based on similarity of the propensity, i.e. the probability that they're going to have a given treatment. And so if you were to group people who have the same propensity for treatment it may well be that a 99-year-old female and a 24-year-old male might have the same probability of treatment and be binned together in propensity scoring, and it wouldn't make biological sense to compare them. So this new approach that we've been working with collaborators, Bob Obenchain and Stan Young, who are longtime collaborators. I actually worked with Stan Young as a graduate student back at Duke in the 90s, and they've published a body of literature, and I've recently published another thing on with them that's actually forthcoming. And the idea is we want to cluster patients by similarity of pretreatment covariates and compare outcomes among like patients. And the work that we're going to show next is not yet published, but it's we've extended these approaches to survival. Because it wasn't yet published, we were going to hold back on that for our bipolar disorders. You want some tried and true methods for your, but in the spirit of OHDSI, where we also want to look at multiple methods, we expect to ultimately publish a reanalysis of the data using these new methods. So the basic idea of local control is you're essentially creating a local group of patients that you're controlling for covariates, and you compare them, the treatment outcomes. So you have a treatment 1 that's in blue and a treatment 0 in red, and we create, this is just a toy data set where we said the patients with treatment blue are going to be younger and lower body mass index, and we're on average, and we're more likely to give the red treatment to older patients with a higher body mass index. So if you're thinking of some sort of outcome, and the intensity of the color, the brighter the color, the better they do, you'd expect younger, lower body mass index people to just do better on average, but you see way more blue dots. And so the problem is if you naively compared these groups, you'd say, well, oh, the blue drug is much better because we see much fewer patients who do worse on blue. So this is not the same data set, but this is actually a real data set comparing costs where we see a red treatment and a blue treatment, and the cost of treatment was $207 on average higher for blue than red. And so I'm showing this graph because often you need to think in terms of treatment differences. You're going to compare the outcomes of one group versus another. So you can have a big cost of $10,000, $12,000, and you're looking at the delta among the two groups. So if you look uncorrected for bias, you get an estimate of $207. But as you shrink and look at smaller enclosing radii, and I'll show this on the next slide, you get a corrected treatment difference that could be as low as minus $462, where the red and the blue lines have flipped, and the red treatment's actually more expensive. So there was a bias in that one treatment was more likely to be given to people who would do worse. And so I have an animation here which shows an example here of the earlier data set, not cost data, but rather the red versus blue, age versus body mass index. So what we see here is in the dotted lines is the uncorrected Kaplan-Meier survival curve, and the red line falls quicker, and we can say this is actually people, a larger fraction of the patients dying under the red treatment when you look naively. As we take our method and look at smaller subgroups and basically create local survival curves within each subgroup, we're able to get a correction, a bias-corrected Kaplan-Meier curve where you get all the intuition of that Kaplan-Meier survival curve, but correct for the covariates. So on the next slide, one of the questions people ask, well, how do you decide what variables to use? And the steps are as follows. You want to find variables correlated with choice of treatment. Perform a sensitivity analysis as to whether a variable affects the treatment difference comparison, and then retain only the variables that are relevant. So I'm going to show an example that might best be described just looking at the picture. Again, a red and a blue treatment. The ideal dosage is one that corresponds after some normalization with one's weight. And so the ideal dosage is following this line. Again, the fainter line, dots are patients doing worse, and the brighter dots are patients doing better. And all we did was made it so that the variance was higher for the blue than the red. And so on average, blue patients are doing worse. Here's a histogram of the outcomes of the blue versus the red. This dotted line is the mean, and it's 12.06 is the mean of the blue, and 4.01 is the mean of the red. So naively, it would suggest that the treatment difference is 8 units. Now, in the simulation, there is no treatment difference, i.e., if you the outcome is simply the absolute value of the difference of the ideal treatment to the target treatment, which is fitting this line. So I made the points a little sparser here to make this graph visualizable. But what we do is we in addition to the weight and dosage, we put in 2 noise terms. And this binary vector here says what variables we put into the local control analysis for bias correction. So if it's all zeros, which is this black line, there's no treatment bias correction. Or if it's only the noise terms and none of the either weight or dosage, we also see them falling along this line. The blue lines here is when we just included, I think it's dosage, and the purple lines when we use both. If we included the noise terms, it didn't detract from us getting this treatment correction, and so you can see again as we look at smaller subgroups of similar patients, each patient forming the centroid of their own local neighborhood, their own sort of survival curve of near neighbors, we're able to get a proper estimate, which is there is no adverse drug reaction difference between the two drugs. It was simply a result of that one population had much poorer dosing, a lot higher variance in dosing. And so you can take this type of thing and look at all possibilities, do a full factorial analysis, and you see that, again, dosage, weight, there's a weight-dosage interaction, and weight itself are all that's relevant, and none of these noise terms are relevant to fixing the biases. So one could say safely, okay, well, we should include dosage and weight as variables. So here's another example to make this more concrete. So we found some Framingham data that was on the internet, and they looked at different cardiovascular outcomes for a 24-year study. And this plot here, there is of the cumulative incidence of hypertension with the competing risk of death. So death could also occur before you get hypertension or before the study ended. And so we looked at the dosage here of smoking. So there's the dotted lines are non-smokers. The heavy dashed lines are the light smokers, and the solid line are the heavy smokers. So we see an interesting phenomena where it looks like non-smokers have the highest hypertension, heavy smokers less, and light smokers do the best. Now in terms of death, it's better to not smoke, of course, which is here. So what we did then is we said, well, let's show here again the uncorrected model, cumulative incidence, and then we look at correcting for sex, heart rate, body mass index, blood pressure, age, glucose, cholesterol at enrollment. These are all measures that were available. And so whether we use the local control method or the competing risk method, we see that heavy smokers and non-smokers have comparable hypertension, but actually light smokers appear to have less hypertension. Now this doesn't say go smoking lightly because we still have the problem of death by other causes. So, and these results actually are consistent with some publications, so this is not earth-shattering. There's understandings of what nicotine does in terms of vasodilation, constriction, etc. But the point is, one cannot naively plot cumulative incidence or Kaplan-Meier curves without addressing the biases, and we get a much more nuanced view. Comparing the two methods, we actually see that, again, when we fit the more linear model of a competing risk curve, you lose some of the nuance of the crossings and so forth that go on with the data. But overall, there's a consistency in the methodology showing that, yes, light smoking or non-smokers have the lowest risk of death, and the light smokers have the lowest hypertension. There may be some. One of the reasons, by the way, that the BMI is one of the big variables, that by smoking, apparently, you tend to have a lower body mass index. People, I guess, are smoking instead of eating on average more. So that's one of the reasons why BMI is so important, but all these other variables were important for correction. And then finally, we took a little different cohort here than in the publication. We added children, and why I did was there's a particularly big bias in the data where risperidone is given with much higher probability to children in this cohort. And so here's the uncorrected data, and here's the competing risk regression, and then here is the local control regression. Interestingly, you look at this, you say, well, what correction has occurred? Well, this line has come down a fair amount with lithium, but you also see that if you were to kind of draw a smooth line with this, you'd see it really does correspond to this. So you do lose some nuance when you go to a linear regression, competing risk regression model, whereas you see, there's this build up and then apparently a plateauing of hypothyroidism cases after a couple of years for lithium, which accounts for why this is lower in the averaged regression model. So I'd like to thank my collaborators here at UNM, Los Alamos, Montana State, UCLA, New Mexico Behavioral Institute, National Institute of Physical Sciences, and finally, of course, the Reagan-Udall Foundation, the NIH, who's made this research resource of data and a laboratory computational platform to do this work in has been really invaluable. And with that, I'd like to open the floor for questions. We're going to unmute your microphones, and you can talk on the mic, or if you're more comfortable just clicking on the chat and asking a question that way, we'll also take questions via the chat. So thank you so much, and look forward to your questions.
Great. Thank you, Dr. Lambert, for presenting to us. So like Dr. Lambert said, I will be unmuting. So if you'd like to speak, please just announce yourself first, and then feel free to do so.
The conference has been unmuted.
Great. Any questions or comments from anyone?
Christophe, this is Alec Walker. This is a wonderful presentation. I'm going to go back and read the references and look for your paper when it comes out. I have a question about selecting the population on the basis of having had a thyroid test. It seems to me that if somebody develops clinical hypothyroidism even if they haven't been tested, they will get a test because of their clinical presentation.
Exactly.
And then they would into the cohort on account of that test.
Yeah, and that's we write about this in our paper. So there's increased testing due to standard operating procedure, if you will, and then there's increased testing due to the potential of it just showing up more often. In other words, you see symptoms, and so you test the patient. And unfortunately, you can't disentangle those two from the data, or at least we weren't able to. Maybe there are some other covariates we could. So we, therefore, in our paper, we presented two models, one without adjusting for that and one with. And it didn't change the results so dramatically. I forget the exact number now, but it went up from, let's see, I think we said like 1.3 to 9 times higher, went to like 1.52 or something. Don't quote me on that number, like the lithium versus the others. So we were concerned about that, and yes, it's a very valid concern, and so that's why we, and I should have probably showed it in the talk, the two models. Does that answer the question, or?
Yes, it does. And I just look forward to seeing the two models and understanding how that adjustment works.
There was a question on the chat, how did you calculate adjustment incidence rate, such as SAS procedures? So the question is, I used the CMP RSK package from in R, which is open and available. So it can be kind of slow to compute sometimes, but it's pretty good. There's also some other stuff I didn't show where we tested for time varying covariates and stuff like that, and presented the Schoenfeld residuals that show that there didn't appear to be evidence of time varying covariates. We plan, by the way, shortly to make the local control package available in R via the CRAN archive. So we're writing up our paper right now on that, and hope to submit it soon. And then you can apply these methods to your own data if you wish. Other questions?
Hi, this is Ming Yu. I want to ask you, is it possible to get these results using SAS software?
Yes, I'm not a SAS user, but it's called, oh gosh, there is a proc for that, for competing risks regression, and I just apologize, it slips my mind the name of it. I think a Google search would quickly find it. SAS competing risks regression. Let's see. PHREG is the SAS procedure that does the comparable fine and gray competing risk regression model.
Oh, okay, thank you.
You're welcome.
Yeah, when you calculate the cumulative adjusted incidence rates, do you have a flexible follow-up or fixed follow-up?
Flexible follow-up or fixed? I'm not sure I understand what you mean by flexible and fixed.
I'm sorry, I mean flexible, the time period is flexible or fixed follow-up?
So as I described, probably went by fast on the data staging, the time to event is a variable, and the event type's a variable. And so the data varied from, somebody getting hypothyroidism on day 1 up to, the longest time that we saw, which I think was 10.3 years. We had one person who actually was on monotherapy without a break in 30 days for 10 years or something like that. And so with the nice, and I'm glad you asked that, because a really important point, a lot of data staging that's done for electronic health record, administrative claims data, says let's take a fixed time period that we observe stuff, start treatment and look what happened over 2 years, say. you have to drop all the patients that didn't make it 2 years. And that, in a way, is an observation bias where there could be important medical reasons why you couldn't see them for 2 years on a treatment. And so the advantage of survival analysis is someone's contribution of 6 weeks of observation, what happened or didn't happen in terms of hypothyroidism, contributes to the curve for the first 6 weeks. Then it drops out of the summation, and the patients that made it further contribute to the rest of the estimate.
Yeah, thank you. And for the incidence rate, did you just look at first event, or you look at the subsequent events too?
So it was just the first event of hypothyroidism or ending monotherapy.
Oh.
So yeah, there are such things as multi-state models that one can try to, more like a Markovian process that you could try to model this type of data. Mm-hmm. And that would be an interesting area for research of how you do that and adjust for biases. The challenge is if you go to multi-state models and you're looking at state transitions, you quickly sort of fork the population into smaller subgroups, and you can kind of run out of sample size sometimes. So
yeah, that's true. Yeah, and you also I think have cost results. I think there's survival results, cost results. They're probably different type of distribution. Did you?
Yeah. Well, I kind of mixed different things. When I was talking about methodology,
mm-hmm.
I was just showing there's, Obenchain et al. At one of his local control papers, he looked at major depressive disorder, and he was comparing cost of treatment, and we used that data. It was a cross-sectional type analysis, not a survival analysis. And so we've taken these approaches to both of those settings.
Okay, and then see when you use competing model, this is new to me. And then when you look at cost, you look at cost per year or per month. How did you?
Well, we didn't use competing risks for the cost model.
Uh-huh.
It was just the hypothyroidism and the smoking model.
Yeah. And then in the cost, you have this corrected difference between treatment groups. How did you do the?
So that was 2 drugs, right?
Mm-hmm.
And then there was different pretreatment characteristics. I didn't go into the details. I mainly wanted to show the idea that we're looking at a difference in treatment. So one of the things I didn't talk about with local control is once you've corrected for the biases, you can take the treatment difference per patient, like take a patient's, what cluster that patient falls into, that neighborhood, and take the treatment A versus treatment B difference, create a new covariate, and go and now analyze your patient data, and then look at heterogeneity of treatment effect of the treatment differences. So you've sucked out the biases, at least the ones you've been able to characterize. There could be unmeasured ones. And then you can look at how the covariates modulate the difference in outcomes for a pair of treatments.
Yeah.
Maybe we could allow anyone else to ask questions, Min.
All right. Yeah. Okay.
And if there are any. If not, we can. Is anyone else? Well, back to you, man. You get the last question. We're right at the top of the hour here.
Yeah. When you look at the difference in cost, what models did you use for the correction?
That was the local control methodology,
mm-hmm.
and it's basically looking at the difference in cost in all these local neighborhoods, and you average over all those neighborhoods to get an estimate. And the covariates, I didn't describe what they were, but they were different aspects of features of the patients, whether they had a heart stent, things like that.
Oh, okay. So you did it in R, not SAS, right?
Yeah.
Yeah.
I did it all in R.
Yeah. So for this local control, is there a similar procedure in SAS?
No.
I'm sorry. So it's a little past noon. So if it's okay with everyone, I think we can, Dr. Lambert, if you want to just quickly answer the questions, and then I think we can go ahead and end the meeting, since I don't want to, take up too much of everyone's time.
Yes, there is a deprecated version called USPS in R, and we're releasing a new one. There's also a JUMP routine developed by SAS. You're probably familiar with the JUMP package, and they developed a version of local control. And so we can let you know if and when we get another out.
Okay.
So I'd like to thank you all again for your attendance and your engagement, and feel free to contact me if you like. My email is cglambert@unm.edu, and if you'd like to discuss things further. So thanks again, Christine, for this opportunity to present, and for the wonderful resource of IMEDS.
Great, thank you.
Thank
And
you.
so our next community call will be on Friday, May 20th. So you'll be seeing an email from us with the topic of that discussion soon. So again, thank you all very much, and have a great